We have been talking about buffers, and we've done several buffer calculations. And so now we just want to look at it systematically and think about some steps you can think through. First thing you always want to do is think about what you're given and think like a chemist. You want to think, what is there in the beaker? How will those things interact with any added acid or base? So think about what you have. We want to think about, is the buffer acidic or basic? You can think about your Henderson-Hasselbalch equation. pH equals pKa plus the log of the conjugate base over the acid, or the similar expression using pKb. And now, if you know your Ka value for the acid and those ratios, you can figure out where your pH value will fall. Will this be a buffer with a pH in the acidic region, less than 7, or basic? Then, that's the first step, and if you just have a buffer solution, you probably have now finished the problem. But if you have a buffer solution to which you've added additional acid or base, you are going to have to complete that neutralization reaction, because adding that acid or base is going to affect this ratio and hence affect your pH. And remember, when we have a neutralization reaction, you have an acid plus a base forming a salt and water. And in the case of a buffer system, the acid or base that's reacting is a weak acid or base. So if you think about the situation where we add a strong base, it will react with the acid. So this would be a weak acid in our buffer solution. And so we know that the salt will have the conjugate base. And so notice that as we add that strong base, let's say we add sodium hydroxide, it uses up part of our weak acid, makes more of the conjugate base, and hence it affects our ratio and our pH. So you will have to solve, using your Rice table, your stoichiometry, that acid-base neutralization reaction. Let's look at an example. Okay, so here we have a question where we're asking you to pick a buffer solution that would have a pH of more than 9. And we have 4 different situations, all of which have equal molar amounts of the acid and the conjugate base. So let's just take a look at the first one. Notice that we are given a pKb value, so we can think about our Henderson-Hasselbalch equation. We know that in all of these cases, our ratio is 1, and hence that whole log value is going to go to 0. So in this case, our pOH is just equal to our pKb, and if we solve that, we find that that is 3.2, and remember, that's the pOH. We want the pH, and so our pH would equal 10.8. Now, we've already found our answer here. Here is a good buffer system. Okay, but let's look at just doing this with approximations to make this faster. If we look at answer choice B, the Kb is 3.8 times 10 to the negative 10th. Well, for a quick approximation, we could look at that and say the pOH will be the negative log of 3.8 times 10 to the negative 10th, or it'll be around 10. Okay, that won't be exact. Okay, it's going to be more like 9.4, but around 10, so we know that our pH will be around 4. That would not be a good choice for a system that needs a alkaline system. Okay, for answer choice C, we can say our pH is going to be close to 2. Okay, we could calculate an exact value, but for this, just trying to find the right system, we don't need to. And our pH would be around 8 here. Note that we do need to oftentimes calculate exact values, because these are logarithms that a difference between, say, a pH of 10.8 and a pH of 10 can have a big change in the actual concentrations. So So you do need to be able to do that. But in this case, we can at least make a quick approximation and figure out that our answer is A. In an acid-base titration, we're generally trying to determine either the concentration or the Ka, Kb values for an unknown acid or base. If we look at an example of titration curves, so our setup for a titration is we generally have an acid or a base in which we do not know the concentration or the Ka, Kb value. And then we have a strong acid or base. So here we are taking the strong base and we are adding a strong acid. And for that titrant, the thing we're adding, we need to know the concentration and the volume very, very, very accurately. Now looking at our curve here, we see that initially, before we add any acid, we have a very, very high pH value. That makes sense. We have just a base. We expect that to have a high pH value. As we start to add the acid, we see that our pH value stays high for a while. And if we think about our neutralization reaction, acid plus base goes to salt plus water. At those initial points, points A, B, and C up there, we still have excess strong base. Remember that our hydroxide and hydronium concentrations are linked. So when we have excess base, we have a lot of hydroxide and very little hydronium. That's 10 to the negative 14th there. And we know that our pH is the negative log of that hydronium ion concentration. Now then we see, as we get near the equivalence point, the point at which we have equal amounts of acid and base, assuming we have a monoprotic acid, so something like HA and let's say NaOH. Okay, so we have equal amounts of acidic hydrogens and our hydroxide right here. Okay. And at that point, we have neutralized all of the base, and we have just our salt and water. And our salt, since it is the conjugate of strong acid, strong base, since its ions are the conjugate of those, it does not act as an acid or base. It's going to be neutral. So we should end up at pH 7. And as we move further down here, now we have added excess acid. And so, as we would expect, the pH is very low. Now if we compare this chart, and here now we are looking at a strong acid titrated with a strong base, and we compare it to the one on the right, you see several differences. And a key difference here is notice that our equivalence point now is up here at pH 9. Our equivalence point is no longer neutral. Notice that in both cases we're starting with an acid, but the difference is that the chart on the right is a weak acid. So now we have a weak acid. Our titrant, what we're adding to it, will generally always be strong. So we're going to have a weak acid plus our strong base. Okay, you're still going to get a salt and water. But notice that in this case, one of the ions in the salt will be the conjugate base of that weak acid. So this will contain our conjugate base. So as we start adding strong base and we start neutralizing some of our original weak acid, notice now we have a buffer system. We have something right here that contains both the HA, the acid, and the conjugate base. Okay, so we set up that buffer system. Now, as we get to that equivalence point, the point at which we have equal moles of the acid and the strong base, so that we get to the point where we have just the salt and the water, notice now we have just the salt and the water, but that salt contains our conjugate base. So it makes sense now that our equivalence point is at a pH above 7. Okay? Up here now, we've added excess base, So our pH goes up really high. Think about that point though, that equivalence point for a moment. Now we have just that conjugate base. And we know that that conjugate base can react with water in an equilibrium reaction, okay, to form that OH, hence our pH is above 7. And notice now a couple things. We can use our Ka expression that should be HA, HA. Okay. At this point, we can use our Ka expression to figure out things like the pOH at the or the pH at the equivalence point. And I want you to think about this buffer situation for a minute. We have a equation for our buffer situation. pH equals pKa plus the log A minus over HA. So thinking back to this area where we have a buffer situation, notice that we can figure out the pKa because we know right here how much base it took to get us to the equivalence point. That's when we've used up all of the acid. But notice that when we've added half that much base, in this case at 25 milliliters, we would have used up only half the acid, and we would have made an equal amount of the conjugate base. So at that point, the A minus over HA ratio is 1, and the pH is simply the pKa. So at the half equivalence point, we can come over here on our graph, and we can look at the pH value, and suddenly we know the pKa for that acid.